All right, I'm going to try another video solution people are asking about here. Let's try number 17. It says, how much gravitational potential energy relative to the ground on which it is built is stored in the Great Pyramid, given that its mass is about 7 times 10 to the ninth kilograms, and its center of mass is 36.5 meters above the surrounding ground. Now, I want to begin by just saying, okay, this is a good starting problem for this chapter, where I can begin by saying, okay, what was the equation of the gravitational potential energy? And I keep calling it MGY. Your book uses MGH. But what's important is two things. One is the formula, so we can use it in more complicated problems. But then two, notice then that it is some height above some other point. So it's relative to something. Somewhere you have to call zero. And I just want to emphasize that we have that freedom of choice. Just once chosen, it has power over us. So we must stick to that for the rest of the problem, wherever you want to call zero. Now, in this problem, they tell us where to pick it. They say relative to the ground. So the pyramid itself is already, a certain distance above, say, sea level. And then, of course, sea level is a certain distance above, and so you can go on and calculate different numbers based upon your reference point, but it is in connection with some kind of reference point for the whole problem. And so they say given relative to the ground, which is really all we can do in this anyways, just by the numbers they give us. So there's not a whole lot we could really mess up on this problem. It is a lot of mass, and it is pretty high. And of course, because of that, it is a lot of energy. And so it's not so much the number here as the formula and the thinking and some other things here. But let me start here with the 7 billion kilograms, and then times 9.8, and then times the 36.5, coming up with 2.50 times 10 to the 12. And the units here would be a Newton times a meter, which is a joule. And so there's the amount of energy in the units that we're used to joule. And so I wanted you to also see the units. Okay, but another interesting thing on this is part B. It says, how does this compare with our daily food intake? And by the way, maybe this is also a good time to mention that, with a lot of mass stacked up, it can be a lot of energy. And you'll see this. You already see the energy here. But this is one of I think, the neatest, latest alternative energy sources. You put up these giant solar panels, and during the daytime, especially around noon where the sun is really bright, it runs this crane that picks up these heavy blocks and just kind of stacks them. And so you've got heavy blocks down on the ground, and then you pick them up, and maybe they're already a platform, so you put it here, then you put it here, and you put it here, and you have a whole series of these. So then when the sun gets low or it gets nighttime, the crane can move over, also charges a bunch of batteries down here. Then the crane can reach over and then let this kind of unwind on a cable system, undoing its potential energy and turning a turbine and making electricity, which runs people's lights at night, even though the sun's not up. So it's indirectly running solar power. And it seems to be the answer to efficiency. It seems to work better than, say, pumping water up a hill and then letting water run downhill and turn a turbine. And so it's kind of neat. And haven't seen one in action yet. I don't think we're quite there, but I think that's going to be the future, where instead of seeing these giant windmills blowing in the wind during the daytime, or since they're so dependent upon the wind, which varies. We'll just stack them, and out in the desert would be a good spot because there's a good, strong chance of having lots of sunshine than there is having wind at given moments. Anyways, I digress here. So let me move on here to B. And then B says, how does this compare to the daily food intake? And again, like the units on joules, I wanted to do this so I can point out that a typical daily intake is about 2,000 calories. And I'm going to write it with a capital C because 2,000 calories with a capital C and so these are calories, but is by a nutritionist. That is equal to 1,000 little calories, as defined by a scientist. And you guys being in the life science, that's good to recognize and to know here that there are two definitions of calories. And the one with the capital C is 1,000 times bigger. Now, we as scientists don't care for the capital C because we use the prefixes. And so 2,000 kilocalories is 1,000 times 1,000 little calories. So that makes 2 million little calories. Now, even then is not a unit of, well, it is a unit of energy, and yes, scientists like it, and yes, it has its advantages and disadvantages, but we want to compare it here, and the unit of a calorie is still used a lot because if you're warming something, the definition of a little calorie is the amount of energy to warm up 1 gram, 1 degree Celsius, and so a lot of our chemistry is done in water, and particularly biology and chemistry. And so the small calorie is real nice, but it is a conversion factor, and this was some of Joule's great work. He was able then to connect mechanical energy, measured in joules, with the chemists and the heat energy with the calorie, and he was able to measure them and come out that 4.186 joules is 1 calorie. All right, so this would be, and I'm going to put it as 2 million into my calculator times 4.186. And so this comes out to be 8.37 times 10 to the 1, 2, 3, 4, 5, 6 joules. So little more than 8 million joules of energy is needed by a human. It's interesting to me always of how much energy there really is in chemical energy in the food we have. Of course, then when you think about it, that's not too much of a surprise given that, a tank of gasoline can make a car go 400 or 500 miles. And that really is just old biological material and is loaded with energy. And so there's a lot of energy in the chemical makeup of our food. And of course, that's, like I said, what makes up our fossil fuels. Okay, but that's now being said here. It says, how they phrase it, how much energy does this compare? Maybe I'll just say, how many, people could this much energy be used? And so we'll take a look here, see how many times we can divide them together. So I'll take this top number and divide it by this lower number, and it looks like we're in the neighborhood of 300,000. So this what sounded like an enormous amount of energy, and it is, but it also is comparison to an enormous amount of energy that one person would need. And so it's 300,000 people would use this much energy in one day. And 300,000. I was just thinking California's, let's see, if I multiply by 10 and 10 again, would be 30 million. California's about 39 million. So roughly, we would have 100 groups of 300,000. So if we had 100 groups of this energy, that's how much energy would be needed for all the people in California in one day. And that's just one day. All right. Well, I hope that is helpful. Bye.